Welcome. Thank you for coming to what will be an interesting lunchtime for all of us. I'm Jenny Muston from Rockpanel, part of the ROCKWOOL group. We're joined by Professor Chris Gorse from Leeds University and Martin Wrigley on the left-hand side from ROCKWOOL. Chris is Director of the Leeds Sustainability Institute and Professor of Construction and Project Management at Leeds. Chris has written articles surrounding the quality of builds pre and post Grenfell, which is why we've asked him to present today. Thank you, Chris, for joining us. Chris will hand over to Martin after his presentation. Prepare to be wowed with the main presentation today, Fire Safety in Buildings over 18 metres. This is not a new seminar for ROCKWOOL post-Grenfell. This is a presentation that's been close to the hearts for some time. I will then wrap up the presentations with a very short but an enlightening tour of approved Document B. If I might hand over to Chris now.
Thank you, Jenny. The lecture or the presentation that I'm going to make today was put together by myself and John Sturges. John Sturges is a materials scientist who I work alongside and for many years taught fire studies at Leeds University. Probably one of the interesting points to make first is we stopped that course in 2007. So we stopped it because obviously it was no longer recruiting students. And fire safety in this country was no longer given the same concern as it was previously. So for me, what the starting message that we have there is we did not expect Grenfell to happen in the UK. It is not what happens with buildings. Our standards, our building regulations are far better than that. But clearly there's an oversight, and clearly it did happen with devastating effects. And we do need to go back and look at what the regulations say and whether we have clarity in what we're doing and the way that we operate and maintain buildings. First of all, Grenfell was obviously a refurbished building, so it's not just the cladding. There are many factors that need to be considered. Nevertheless, the aluminium composite material cladding, particularly the polyethylene or the polyurethane, had a part in the combustion. So a point that we first should note is that the fire within Grenfell spread vertically and laterally. And notwithstanding what is happening with the inquiry, which many people are speculating on, there are a few things that we can see with Grenfell. We can see that the fire both spread up the surfaces of the building and then across and through the building. So there was neglect in many parts to what happened during the refurbishment and the compartmentation that exists within the structure. The other thing to note is we've not demolished the structure. It's quite clear that it has a structural integrity that made buildings like that and buildings that we still have worthy of construction and retrofitting. But what we also must do in the future is ensure that they do have the necessary fire regulations, fire remedial action in place to ensure that they're safe. So if it had been a risk to health and safety in the structure, we would have been demolishing that now. But it is still standing, and whether it gets demolished in the future or not remains to be seen. But what we should note is that these buildings are worth refurbishing if we do it properly. So hundreds of buildings are considered to be at risk, and the cladding systems have been condemned. We've seen many buildings not around us. We've seen student properties no longer occupied because we can't get in the indemnity for the insurance. So we're seeing a period where we're actually trying to come to terms with what we should be doing with buildings of this type. It's also interesting to note that aluminium composite cladding materials in the US are restricted above 22 metres high. And also above 15 metres are not permitted under the Scottish regulations. This is really some of the notes that John would have presented, but just as basic principles, for combustion to take place, we need 3 essential ingredients: fuel, air, oxygen, and the initial sort of heat to allow the combustion to take place. So the fire tests have evolved over a number of years, and we've gone from testing individual materials and looking at the material and how much heat is produced from combustion. We've looked at surface spread of flame, and we've also looked at the chemical species produced from the fire. And from that, we've gone from the single samples to really what is the research that's led to the latest philosophy of testing that the BRE have adopted. But researchers for a long time have been recommending that we should be replicating the conditions of the full structure in order to see whether or not the risks of cladding systems or materials on buildings burning is real. Probably what is interesting when considering the nature of the materials that we're using and whether or not there are risks are the actual sort of principles of fire and how fire ignites. So just before I came here, I was having a number of discussions with John Sturges, who is unable to get over with us, and other chemical scientists that we've got at Leeds Beckett. And we were talking about the fact that I was coming over here and just going over some of these notes. But the Navier-Stokes equation is basically the equation which gives us the properties and things that happen during combustion with the gases. So should any external material catch fire, we know that hot gases are going to be produced by combustion. These will rise due to natural buoyancy. And whenever a fluid or liquid or gas contacts the solid surface, a boundary layer of the material attaches itself to the solid. So that's when we've got a material such as your polyurethane or the aluminium, which just starts to burn, and we've got this this boundary layer of gases or fluid, which is then combustible. This, as I was explained to, is the difference between what happened in the 9/11, where the fire actually went out of the building, and in Grenfell what we saw was the fire travelling up the sides of the building. So if the material at the sides of the building had not been combustible, we wouldn't have had this attraction that we saw, where actually the flames were coming out of the building, then sticking to the surface, and then subsequently igniting and further delivering heat to the remaining parts of the building. So as a result of forces of molecular attraction, so Van der Waals forces, which are distance dependent, interaction between the atoms and the molecules creates this attraction due to the gases that are being produced by the combustible material. What is also interesting is that as a result of the fire, the volatile organic compounds burn, and the gases that are given off end up being a reducing agent which can strip the oxide layer off things like aluminium cladding. And once that oxide layer is stripped off of the surface of these materials, aluminium and other materials are reactive materials, potentially melting or aiding the combustion. So we should pay much more attention to the materials that we're choosing and actually what happens to them during combustion. And at the moment, many of the tests that we're conducting through the BRE and other tests are not necessarily going to pick these features up. So they are going to test them to see how they perform or how the fire spreads. But there are some things that we must learn both from Grenfell and how we move forward and how we put materials together. So in Grenfell, getting back to the construction, we got an insulation layer that was fitted to the outer concrete wall, and there was a gap between the insulation and the outermost aluminium panel. So vitally important is that the combustible material is protected from contact from the heat or the flame, which it was not within the Grenfell situation. So the method that we see for doing this is by fire stopping or filling the gaps with non-combustible material. Now there are some photographs of Grenfell which we will have a look at on the next slide. But one of the things that was pointed out to me that there were some inadequate construction details on the refurbishment project. And these construction details are probably typical of most refurbishment contracts. So when the design's produced, there's a lot of unknowns with the structure. And somebody said to me that there was no detail for the fixing around the cladding. Well, clearly this detail that we've shown here was not how the actual cladding was fixed, how the sills were fixed, because there's no fixing shown. So when I was showing details like this and we're critical of them, actually if we were constructing this, we would normally be having discussions on how we fill these gaps and how we address these on site, and looking at the details depending on actually how the structure lines up with the cladding, the proposed cladding. What we have to do in future is ensure that there are adequate seals between the sills and the cladding materials, and the fixing details are clear. If I'd have inspected this building prior to the fire, whilst it is clearly notable that there are gaps in the fire barriers, the fire stopping, it's probably not as obvious that some of the other fire barriers are missing. So some of the vertical fire barriers appear to be missing. And it may be, as the photograph looks, that the actual fire stops are fitted onto the insulation rather than back through to the actual fabric of the building. I put to you that practice to this on other buildings is probably common. So certainly when we test our buildings and we do building physics for thermal performance, we often get air leakage or we get smoke passing from one building to the other. That would not happen if fire barriers were in place. So we know that both on the domestic building stock and on commercial building stock, this situation probably arises in most of the buildings that we've built, but can't go on in the future. So we must pay much more attention to ensuring that the fire stops are in place, they're adequate, and they do prevent the combustion moving without resistance. So we can see there that we have got gaps, and it does appear that the fire stop is fixed to the face of a combustible material. The other problem that we've got in terms of actually tackling this fire is that once the fire took hold, it was a combustible material, but there's actually a low thermal diffusivity on the insulation, which means it actually resists the passage of heat, which has actually prolonged the burning. Because there's obviously a lot of fuel there, there is the potential to keep that fire going, but it actually becomes a source of combustion that is going to take place over a long period of time and almost protect itself from being extinguished. So the material being combustible and insulation material brings some problems in its own right. This is why, going back, this is why the standards, the building regulations have always been upheld as ones which place fire first. It is the reason that they came into force. So under the London Building Act, as a result of the Great Fire of London, we brought the regulations in place. So worldwide we're regarded as people holding some of the highest standards in our regulations and standards. However, we have let that slip. I was asked to do a review for the CIOB's Research and Innovation magazine or journal, and I was asked to go through some of the regulations and suggest why the industry had got to a situation where it had. And it was not until this point that we'd really sort of examined the building regulations in any detail. So when you look at approved document B, bearing in mind I'm an academic, I have access to all of the other subsidiary documents, the guides and the other standards that you refer to. I found it extremely confusing, extremely time consuming to try to untangle what certain very pertinent and vital terms meant within the regulations. And I put it to you that as a professional who's currently in practice, that you don't have the time to go through the regulations and to do what I did. I did it specifically as a study, and it probably took me about a week of half a day every day going through the regulations and accessing documents to realise that there were some conflicting terms and that it just wasn't possible to get easy interpretation of the regulations. Counteract that to 25 years ago when I came as a student studying construction. The building regulations were relatively simple, straightforward documents that most people could understand. They were relatively fit for purpose. We have a very disparate industry, so people come in and enter the industry without much experience and training, and yet we expect them to operate to high standards. We do need to move back to regulations that have clarity and serve the purpose that they were intended, which is to provide good guidance. One of the other challenges is a lot of the other documents that I accessed cost between £80 and £200 per document, and I must have accessed 20 documents. So is it even reasonable that we're actually requiring somebody to access potentially £1,000 worth of documents in order to arrive at a definition, not even an understanding of what we should be doing? The point that I would actually try to make is that under the regulations we're all responsible to provide, to ensure that the risk to health and safety is minimised. So this is the key point that I would like to take from the regulations. The external envelope of a building should not provide a medium for fire spread if it is likely to be a risk to health and safety. I say that because I think what this presentation will state is there isn't necessarily clarity in standards now, but actually what we must do is actually start to put the materials and systems together that are safe, and we should be using our own professional judgment to do that in addition to the guidance. So some of the points of contention are the definition of what is meant under Class O under the building regulations, or the Class B S3 D2, which Martin and Jenny will go into more detail later. But coming into this as a building construction expert and not necessarily a fire expert, was trying to understand what the two definitions meant. So in terms of the BS3-2, the S3, the sub-classification, allows for unlimited smoke production, so that gives us free range. And the D2 is the lowest classification for fire droplets. Thus there's no limit to set the smoke production or flame droplets from that current standard. So we're talking about something which is of limited combustibility, which can produce as much smoke as it wants and drop fire on the rest of the structure. So the standard there is, for a general interpretation, is very low. So Class O restricts materials to limited combustibility above 18 metres. But this is what the European or the British Standard European standard is given as an alternative, only limits the spread of flame for a restrictive period. So the spread of flame, if I can refer to my notes, for the non-combustible test was under the surface flame attack, and where required, edge flame attack, cross-referring to another section 6.3s, with 30 seconds exposure time, there shall be no flame spread in excess of 150 millimetres vertically from the point of application of the test flame within a further 60 seconds from the time of application. So what we're referring to is an initial exposure to fire for 30-second period on a sample of material, and that when that flame's been removed, that spread of flame won't increase over that 150 millimetre sample. It doesn't, when you look at that as a test for non-combustibility, that doesn't sound to be a robust test. So what, in my view, if we go back to the first part of the regulations, where we must maintain the risk of spread of flame to reduce the risk to health and safety of the people, whilst we have these tests, these are tests to guide, we still should be looking at what happens in buildings when we put these materials together, Clearly, we've got a problem with aluminium clad panels where there's combustible material inside them. And there may still be some issues with whether or not it's appropriate to use volatile materials if we basically constrict the protective oxide layer off them. That's not my area of expertise, but it's something that really should be looked at in more detail. Something you should look at to make us aware of just how quickly the fire spreads, and a totally different case, but the Dublin Stardust case, probably more important. This was a nightclub where materials within the nightclub, when put together, allowed combustion, which ended up with 48 people losing their lives. But what's more interesting is the fact that when the BRE conducted an experiment to look at that situation and to work out why the materials combusted and why there was such so many people losing their lives, that they set up an experiment which you can see online, that if you follow that YouTube link, where they built a box to replicate the nightclub. They put some seats in it, they put the ceiling tiles and the wall coverings. They set off a small fire, and within the space of about a minute that fire progressed, and the room that they reconstructed was an open-ended room, and they'd got about 10 researchers filming and taking the temperatures of the fire within the room. And due to the speed with which that fire progressed, they fell over themselves trying to get out of an open-ended room. So once we've got combustible materials together within a building, once we start to assemble them and we allow the oxygen to move through those surfaces, and if, as we see by the Navier-Stokes equation, that the gases produced from the combustible material create a fluid that is combustible on the surface of those materials, we're creating paths, oxygen paths and fuel to take the fire rapidly throughout the building and obviously threaten lives. Please do take a look at the Dublin Stardust and the Lanarknowle videos, and there are plenty others that will give you examples of how rapidly fire is spreading through these buildings. We've obviously got to pay a lot of care to the refurbished projects to ensure that the buildings have sufficient compartmentation, that the services are protected. We can't have fire spreading through the buildings internally. Equally, we have seen a lot of fires in Dubai where the fires are spreading up the surface of the buildings. There's been hardly any, I don't think, I can't say for certain, but I don't think there's been any reported loss of lives in these fires. And it's mainly to do with the internal structure of the building. So the compartment within the new buildings has been fit for purpose, as in the combustion has not penetrated back into the building beyond the surface apartments. So there are plenty of buildings, including the address downtown Dubai tower, which happened after Grenfell, where the fires can be seen stripping up the buildings. In some of these buildings, occupation remained while the fire was taking place. There are accounts that one New Year's Eve on one of the buildings, I think it was the Sulphur Tower, that they carried on having the New Year's Eve party while the fire was taking place. I certainly wouldn't have been staying in the building, because you don't know where the building's been compromised. We don't have full control of all the people on site and what they've done. So I think we should be paying much greater attention to detail in terms of the products that we're putting together on our cladding systems. So, as a general guidance, I think the building regulations are confusing, and this has been something I've written about publicly and put to parliamentary inquiries. There is a lack of clarity. However, that doesn't take us off the general requirement that we should be protecting the health and safety of the people within the buildings, and we should be resisting the spread of fire across the surface and through the buildings. The buildings that we've got in the UK generally are structurally sound and can be refurbished adequately, but we must ensure that we've got fire stops properly fitted, that the building work is properly checked. So we've got to have more robust systems for ensuring that the work is taking place. I know that's not easy, because I know I've had work done recently in my own house by people I trusted, and when I've looked at it, it's not been done right. They clearly didn't have the experience that I thought they had. We do put a lot in terms of actually ensuring people are competent, and probably our checks for competency are not always adequate. We must be checking the works that we've had done, certainly the builder's work and any reinstatement. You've got to be paying particular attention to Grenfell, to Lanarkshire, and making sure that materials that we're putting on the faces of our buildings are non-combustible and sufficiently restrict that spread of flame so that we don't get a situation such as Grenfell reoccurring. I've seen Martin's presentation before, and I think it does offer some insight and probably does provide us with products that are certainly robust for most future eventualities, and certainly more robust than the aluminium cladding structure of Grenfell. Thank you for your attention. Thank you.